Second presentation will be remote. It is a talk about reconstructing S boxes from cryptographic tables with MLP by Raghvendra Rohit and Sumanta Sarkar. And Raghvendra will give the talk. Please.
Yeah, so thank you very much for the introduction. And thank you organizers for allowing me to give this talk online. So I'm going to talk about reconstructing S boxes from cryptographic tables with MIL, and this is a joint work with Sumanto Sarkar. Okay, so the first thing, what are the S boxes? So the S boxes are basically a nonlinear mapping. So basically they take M bits as inputs and output N bits in a nonlinear fashion. So in literature, we have seen a lot of S boxes. For example, in case of DES, we have M is 6 and N is 4. For AES, M and N are 8. And for check SCON, we have 5-bit S boxes. For gift and present, we have 4-bit S boxes. Now, if we know the S boxes, then basically we can construct several cryptographic tables, which basically define some security properties. So the first one of them is the difference distribution table. So let's say we have an S box and bit S box, and if we have the input difference alpha and output difference beta, then this behavior we can characterize by the difference distribution table. So this is basically 2n times 2 to the power n matrix, where each entry in that table denotes the number of solutions corresponding to S of x plus S of x plus alpha equals beta. So as you can see the example on the right side. Now the another cryptographic table is the linear approximation table. So basically for an input x to the S box and output S of x, basically we mask input with alpha and output with beta. And then basically we count the number of places, the number of times when beta dot S of x and alpha dot x are equal. The number of times they are equal minus number of times they are not equal. So this is basically defined by the bias. And this bias is characterized by this linear approximation table. Another important table which involves the inverse of the S box is the boomerang connectivity table. So for the input difference A and some uh, some value B, we define the boomerang connectivity table of this S box S at points A and B as basically the number of solutions X, where S inverse S of X plus B plus S inverse S of X plus A plus B equals A. So now there are some other cryptographic tables as well. For example, difference linear connectivity table, autocorrelation table, and some variants of boomerang table like upper boomerang connectivity table and lower boomerang connectivity table. So now the question is, if we know the S boxes, then because we know the direct relationship from S boxes to their tables, so we can directly construct those cryptographic tables. But the other way around is not trivial. So that means if we know one of the cryptographic table T, then how we can reconstruct an S box. So this problem is important because if you can fill the entries of those tables in some specific patterns, then you can find some good S boxes. So this is the problem which we are addressing. But in this work, we are targeting a much more stronger variant of this problem. That is, instead of giving the full table, let's say we are giving some L rows of the table, then can we reconstruct an S box that maps to this partial table T? And even another stronger variant of this problem is, without the knowledge of all the tables, can you find an S box or a Boolean function with a given cryptographic property? For example, let's say you want to find 4 differential uniform S box or an S box with linearity term. So we are in this work, we are aiming to address this problem P1 and P2. So before going into that, let's see some of the existing works and their limitations. So the earlier work was from Bora et al. In DCC 2019 and from Tian et al. In DCC 2020. So their approach is based on the tree-based search approach. So basically they go step by step, and let's say they reach, let's say 10 rows of the DBT, they can find some possible combinations of first 10 values of the S boxes. Now the other values they need to be searched in an exhaustive way. So they cannot solve these two problems. Then there is another work from Dunkelman and Huang from TOS 2019. Again, they cannot solve these two problems. And the most relevant work, uh, which is related to our work is from Lu et al. From DCC 2022. So there they have given this SNT modeling for reconstructing S blocks from DDT and LAT, and their model work up to 5-bit S boxes. And they also gave some results related to differential uniformity, linearity, and fixed points. So in our work, basically we gave the first mixed integer linear programming models for reconstructing S boxes, and thereby we solved this problem P1 and P2. And as an additional contribution, we gave a heuristic technique. Because of using that, we can find some CCZ inequivalent S boxes while preserving some of the cryptographic properties. So in this talk, I will just focus on the digital S box reconstruction. And the other part you can see in our paper. So our input is basically a partial DDT with elbows, and the output of this is either an n-bit S box, or if there is no S box corresponding to that elbows, then the model is infeasible. So this is divided into 4 steps. The first step is we model an S box output with a permutation matrix. Then we model the XOR of the S box output values. And then once we have these XOR values, we map them to the entries of the DDT. And then we solve this with some optimizer tool. So in terms of permutation matrix, so basically it's a binary matrix consisting of zeros and ones. So if you want to represent any integer, so for example, here the 3-bit S box. So if you want to represent this, then 7 basically corresponds to the last entry 1. The same way 6 corresponds to 1. So here you see that the row sum and the column sum is always 1. And using this permutation matrix, we can define the integer value yi as this summation. So now we can define this for any integer value. So here note that yi's are integer values. So now once we have the modeling for this yi, we model the XOR of the SBox output values. So here the main problem comes from the fact that if we know the integer values, then we cannot directly model their XORs. So first thing is we need to decompose them into their binary representation. And then once that is done, we compute the XOR. We model the XOR values. So for example, if the input difference is 1, then we want to model y0 XOR y1. So this output XOR value we model bit by bit. So this variable C, they are basically representing the bits corresponding to y0 XOR y1. So same thing we do for other pairs of input differences. So now once this is done, then we map the values, the variable C with the entries of the DDT. So for that, we use a matrix defined by the input difference alpha. So here W of alpha is 1. So if you see here, if the input difference alpha is 1, then the beta can map to 7 different integers, one of these 7 different integers. So you can see y0 XOR y1 can map either to 1 to 7. So that means the sum of each row has to be 1. Otherwise, we can show that it's not a permutation. And then once that is done, then we connect this yi XOR yj with this matrix W and again with the variable C. So after that is done, we take the column sum, and this column sum is nothing but the entry in the DDT table by 2. So the division by 2 is because we are counting the symmetric solutions only once. So now this model can be tweaked for, let's say we want to find out an S box with difference between complete 2 or 4 by playing with this equality sign. So now coming to the results. So this table denotes the reconstruction problem for the full DDT. So in the column 1, you can see different S boxes, and then we have the model details, and then we are using 2 solvers for this problem. So let's say we have a DDT of 6-bit APN, then this, if we are solving it with the group with 10, then within time limit of 1 hour, it could not give the S box. But the same problem if we are giving to this OR tools from Google, then this gives the S box in 10.31 seconds. So now this is for the full DDT. Now let's see if we decrease the rows, what's the impact? So for APN6, if we are starting with 64 rows, then we can get the S box with differential of 42. If we decrease the number of rows to 49, again we get two differential uniform S box. So this happens till the number of rows are 17. And then once the number of rows are 16, then we see there is a breakpoint where the differential uniformity changed from 2 to 4, and other cryptographic properties are also changed. A similar pattern happens in case of 5-bit inverse, where we see like till 1/4 of the rows are given, then we can have the a similar S box. And then uh, so here till 9 rows, we can reconstruct the same S box. For 8 rows, the differential uniformity and some other properties are changing. So now let's see what are the main observations in these two S box when we APN6 S box when we have 17 rows and 16 rows. So we find these observations. So these two S boxes are very much related. So you see in the blues, the all the 16 elements, they are exactly the same. They are slightly permuted. And also the ones which are denoted in red and green, they are again related, but they are rotated by uh, some offsets. So they are so these two S boxes which we got from 17 and 16 nodes, they are highly related. So if we can reconstruct an S box from the one from 16 rows with the differential in 44, and if we can find some relation that can map from 4 to 2, then it could be interesting. So comparing with Liu et al.'s work, so they try to enumerate all the S boxes, let's say for the present and gift DDT, and their work took around 10 minutes to recover all these 256 S boxes. But in our case, we can do it in 10 seconds. The same thing for Kcheck and SCON S boxes. For them, it took around 6 hours. But in our case, we can get all these 2 to the power 10 S boxes in 10 seconds. And also, in while for this comparison, we used a similar experimental setup. Okay, so now in case of linear approximation table, we have similar results, but note that it is slightly dependent on the tool which you are using. For example, in case of APN6, using Groovy can solve this within 1 minute, but all tools it take around like 10 minutes. So this is again something to see in future how the solvers are actually impacting the performance. So other tables also we have the results in our paper for boomerang connectivity table and difference linear connectivity table. So the another contribution from here, this work was CCZ inequivalent S boxes. So here our main goal was to can we find some CCZ inequivalent S boxes with differential uniformity 4, and they are CCZ inequivalent to the inverse S box. So for that, basically we started with the same differential DDT model, and we introduced some random objectives in the model and we started with 6-bit inverse S box, the initial solution. So for example, you see, we start with the 6-bit, 64-bit random string, and then we create this mixed integer linear programming model for 6-bit S box with differential uniformity 4. And then we gave the 6-bit inverse S box as the initial solution for the model. And then we have this some random object. And then we try to see how this solvers gives the value of this objective function. So yeah, here you can also have some different objective as well, like minimum of this value. You can have a non-linear objective as well. So it is so depending on different objectives, the results will change. But for this objective, if we see the result, then we start with this inverse S box, then the objective value is -94. And then again, it starts increasing the objective values to -88, and then we get another S box S1. So here S0 and S1, they are related, but when the objective value starts increasing for -80, we get another S box S2. So now S2, S3, and S4, we are getting 3 S boxes based on the objective value. So these 3 S boxes, they are related and they are CCZ equivalent to each other, and their differential uniformity is 4. Now, these S2, S3, S4, they are not CCZ inequivalent to S02 and S1. Their property, the differential uniformity is exactly same. So you see, by having some random objective, we can get the CCZ inequivalent S boxes in a few seconds. So in our paper, we have actually found like 4 classes of these CCZ inequivalent S boxes. Okay, so to summarize, basically, we have shown that using mixed integer linear programming, we can reconstruct S boxes from partial cryptographic tables. And we can also find S boxes by tweaking some of these models. And we can find those S boxes with a given cryptographic property and a heuristic method to obtain CCZ inequivalent S boxes. And some of the interesting directions could be can we investigate these heuristics to make this tool more efficient, and whether we can use automated tools for like investigating the classification of like S boxes like affine or extended affine equivalence S boxes. Okay, so to end, I would like to end with this the 6-bit API and difference distribution table. So basically, if you see in uh, in the one of the table where we have seen that only 1/4 of the rows of the DDT are required to reconstruct the uh, 6-bit APM. So now after this work we started, okay, what's the minimal information? So basically from that DDT we can construct another table which have like lot of structural patterns. So the idea was like you replace every 2 by 1 and then you take every I and 32 plus I throw and you XOR them. And then you get replace 0 by some dot for better visual representation. So you see we obtain something like this. So in this table, if you see all the entries within the red block, they're repeated after every 8 times. And the entries within this red and green, they are also have very structural relationship. So here we see that the information is reducing. Uh, so now the interesting thing here is like, what's the minimal information we need to reconstruct 6-bit API? Okay, yeah, so thank you very much. I would end with this.
Thank you, Raghavendra. Are there any questions?
Thank you, Raghav, for the talk. So I have a question. So is it easier to recover S box from a partial DDT compared to recover the S box from a full DDT because less constraints are used here?
Yeah, so the less constraints are used, but if you check the timing, so the timing of the solver starts increasing. So this is one of the limitation.
Raghavendra, did you hear the question?
Yeah, I heard it. So basically the thing is, if you check it here, so the main thing here is it depends on the solver. So if you see here, if you decrease the number of rows, then the timing starts increasing. So it depends on the solver. So it's getting more and more complex in case of partial DDTs or partial tables.
Okay. Does it mean data S box, maybe the space for data S box is very small? If the S box has a large space, maybe in intuition it should be easier.
Yeah.
But I don't know. Yeah. Okay.
Okay. Thank you.
Thank you. Thank you.
Are there any other questions? I have a quick question. Do you think throwing more computing power could make it feasible for larger S boxes?
Slightly, but I think right now it works till 6-bit S boxes. for 7-bit or 8-bit S boxes, definitely if we have more computational power, then it could be much easier, I would say.
Okay, thank you. Let's thank the speaker again.